Okay, so you clicked play, and let's see what happens. In this lesson, Thomas is going to take us through the derivatives of inverse trig functions. This is because we are in the midst of a discussion on transcendental functions. And normally we think log functions and exponential functions, but transcendental functions are all of the functions that cannot be expressed algebraically, and inverse trig functions fall under that banner. So we're going to take a look at the inverse trig functions that you are probably familiar with from pre-calculus, at least to some extent. Like, for example, you well remember that you've got your sine function. It looks like so. Oh gosh, that's ugly over there. But this is nice over here. This is the sine function. And this is very not one-to-one. This is very, very, very not one-to-one. So if you remember from your pre-calculus work, your teacher probably restricted the domain on the sine function to this interval so that the function could be one-to-one. This would be negative pi over 2, this would be pi over 2, this would be negative 1, and that would be 1. And then if I want to find the inverse of that function, it indeed will be a function if we restrict the domain in this way. And if you do that, then the inverse sine function looks oddly like this. This is called the inverse sine function, whose domain goes from negative 1 to 1, and whose range goes from minus pi halves to pi halves. The trick here is that this function is smooth, and smooth functions have derivatives. So we must be able to find the derivative of the inverse sine function, and it's actually not too bad. To find the derivative of the inverse sine function, we recognize that if y is the inverse sine of x, then x is just whatever the sine of y is. And we can take the derivatives on both sides and be fine. The derivative of x is 1. That's not hard. The derivative of cosine y, nope, I'll try that again. The derivative of sine y is cosine y times dy dx, which means dy dx is just 1 over whatever the cosine of y is. Well, that's a dilly of a pickle, isn't it? Because we know what sine y is, but we don't know what cosine y is. So we imagine a right triangle where x over 1 is the sine of y. Well, the cosine of y is adjacent over hypotenuse. What's adjacent? Pythagorean theorem says it's radical 1 minus x squared. That's what Pythagorean theorem says that side is. And so the cosine of y is adjacent over hypotenuse, and that's radical 1 minus x squared, and that is the derivative of the inverse sine function. That is the derivative of the inverse sine function. In a similar way, the derivative of the inverse cosine function is minus 1 over radical 1 minus x squared. It's a similar derivation. You can pull that out in the privacy of your own home. Tan. Well, tangent was one of those jobbies that restricting the domain is pretty straightforward. You just restrict it at negative pi over 2 and pi over 2. This is tan x. If I want the inverse tan function, well, the domain becomes the range. The range becomes the domain, and you get some function that looks like that. This is the inverse tan function. And the curious thing about the inverse tan function is that it is also smooth. And smooth functions have derivatives. We can find the derivative of the inverse tan function by recognizing that if y is the inverse tan of x, then x is the tangent of y. And if x is the tangent of y, then 1 is secant squared y dy dx, which means that dy dx is 1 over whatever secant squared of y is. And here I'll use a different sort of trigonometry that we seem to remember from high school. I remember that tangent squared y plus 1 is secant squared y. Well, I know what tan y is. Tan y is x. So secant squared y is tangent squared y plus 1, and that's the substitution that we make right here. The derivative of the inverse tan function is 1 over 1 plus x squared. And again, that seems to make some sense. The slopes never get wildly big here. Even if x is 0, that's not a very large slope. The slopes get smaller as x gets larger, and as x gets larger in a negative direction, so that makes sense. And the slopes are always positive, and this is always positive. So these are just more things that in theory make sense. Of course, in theory, communism works, so I mean, whatever. Similarly, if you were to find the derivative of the inverse cotan function, you would get minus 1 over 1 plus x squared. That's a nice little thing to have on an index card somewhere. It is not related to this at all, even a little bit. The inverse secant function is just a little bit more weirder a lot. We'll go purple here. The secant function gets restricted in a very bizarre way. It gets restricted to the domain from 0 to pi. This is 1. This y value is negative 1. And so when you find the inverse, there's pi over 2, there's pi, there's negative 1, there's 1. The inverse secant function looks like this. Just weird. This is the inverse secant function. And for reasons that shall become clear in a moment, well, let's do it. Let's actually do it. This is a smooth function. It is a smooth function on its domain, and so it's got a derivative. And so we have to be able to find it. And we're going to find it in the same way by taking the derivative on both sides. So the derivative of secant of something is secant of that something times tangent of that something times dy dx. So dy dx is 1 over secant tangent. Well, secant, that's easy. Tangent, well, let's pull that trig back out. We know that tan squared y plus 1 is secant squared y. And we know that secant squared y is x. So I want to get tan y by itself. So tan squared y is x squared minus 1. So tan y is the square root of x squared minus 1. But I'm not sure if I take the plus or the minus. I'm not sure what we do with that. So here's where the rub comes in. I want to put a plus or minus out in the front, except that sometimes the x's are positive, and that just gets weird. And sometimes the x's are negative, and that gets weird with a plus or a minus in a front. So what do you do with that? Well, if we look at the graph is always increasing regardless of where x is. So I need this answer to come out positive all the time. And the way we do that is to put an absolute value brackets there. We put absolute value brackets there. Because the derivative must always be positive because this function is always increasing. In a similar way, the derivative of the inverse cosecant function is negative 1 over absolute value of x radical x squared minus 1. That's a similar derivation. That is an x. Oh, golly, make this look better, Ritter. You have a master's degree. That's better. Okay, so I mean, we could run through a whole bunch of examples, and that wouldn't be terribly difficult to do. We could run through examples like, let's find some derivatives, like the inverse secant of 2x plus 1. And we would say, ooh, I know how to do that. I know the derivative of inverse secant. That's 1 over absolute value of the thing times the square root of the thing squared minus 1 times the derivative of the thing. And you'd be absolutely right. The thing, the derivative of the thing. You would be absolutely right. Or I might say, let's find the derivative of the inverse sine of sine x. And the derivative of the inverse sine of sine x, well, I know how to do that. The derivative of inverse sine from a couple of slides ago was 1 over the square root of 1 minus the thing squared. And then we would multiply by the derivative of the thing. Well, that's true. The derivative of the inverse sine of the thing is 1 over radical 1 minus thing squared times derivative of thing, and we know that this is the thing and this is the thing. No, that's not true. We need derivative of thing. Derivative of thing. Now, here's the curious part. Some of you who are savvy with trig are saying to yourself, I know what this is. And you're right. This thing is cosine x. Sorry, it's 1 over cosine x. This denominator is cosine x. Well, that's 1. Well, how can that be? If the derivative is 1, then the thing itself, oh, we ought to talk about that when we gather. We ought to talk about that. Oh, that would be super fun. Okay, so I have to let you do that. And we can talk about that when we gather. There's another video in this lesson for my Math222 students about hyperbolic trig derivatives. That's a shorter one, but there are 2 to do for this lesson, my friends. Okay, so there. We'll see you later.